Hello guys, in this video tutorial I will show you how to create the steady simulation of diffuser in ANSYS Fluent, and we will perform these 3 steps. The first step is creation the geometry of this diffuser, the second step is creation the mesh, and third step is perform the simulation in Fluent, creation the boundary condition. So let's open the ANSYS workbench, the student version. You can download it is from official site and save the project in any path. Okay, the first step is creation the geometry. Let's import the model of geometry and open the part design workbench, part design model. Open it. And here let's choose the ZX plane and create the sketch on this Z plane. And for the sketch, let's create the diffuser 2D plane with diffuser, and let's make the millimeters units because the meters is very big values for this. And let's using the sketching tools create the lines of the 2D plane of diffuser. This parallel horizontal line, the diffuser, and horizontal line of the diffuser. And let's create this line, and now let's set the dimensions of our geometry. It will be full dimension 300 millimeters, and the radius of diffuser. Now let's choose the vertical and choose this vertical line. It will be the inlet part of diffuser, 25 millimeters radius. Set the outlet diffuser radius, it will be 35 millimeters. And let's set the horizontal dimensions part of diffuser, 100 millimeters for inlet part, for diffuser part 100 millimeters, and the last part will be also 100 millimeters. So we set these dimensions also, and go to modeling tools and create the revolve operation. Choose the sketch and axis for rotation. Apply and make generate, and now we have the diffuser geometry. And for this diffuser geometry we have to create the faces with names. For inlet we will set the boundary condition for these surfaces. We can create it also in meshing model, but let's create it here. The inlet, outlet, and the last surfaces is walls. It will be wall. Tag this and name wall. Set name. Okay, so now we have the outlet, inlet part, surface, and wall surface. Okay, let's close the DesignModeler and connect it with mesh model. Let's open the mesh model. Wait it some minutes. So here you can see our surfaces with inlet, outlet, and wall, our diffuser. And let's go to mesh and choose the CFD Fluent. It will set some default settings for our geometry. Let's choose the geometry for automatic method, and let's change the method. For example, let's try to tetrahedron smash. For example, we can use the tetrahedrons, multi-zone, and another type of mesh. Let's generate the tetrahedrons, but you can see the tetrahedron mesh, but for our task we have the simple geometry, so we can to create the hexahedral mesh because it's a very good choice for CFD simulation. Let's choose the multi-zone and generate mesh. And how can you see, we have two very simple step for generation of quadratic mesh. This mesh we have to create also the inflations. It is for boundary layers, because we have the turbulent flow in our case. Let's choose the wall. For wall we create the boundary layers and set the number of layers and coefficient of rate these layers. It's created here. Okay, so we have created these boundary layers, and we have the big value of mesh size. Let's decrease some it. I think 5 millimeters is good choice. Let's generate mesh, but for CFD simulation we have okay, our mesh is looks good. Okay, we have the boundary layers on the mesh, on the walls, and let's close the mesh part, and let's connect our mesh with Fluent. Update the mesh. It will export the mesh to the Fluent. After that, we have to open the Fluent, and here just set the number of cores of our CPU for the simulation. Will be used for simulation, of course. My choice is 2 cores of CPU, and now you can see our geometry of diffuser, and for our boundary surfaces, the inlet and outlet, we have the default true settings. Let's choose the turbulence model for our simulation. Let's set the k-epsilon realizable. It more simple turbulence model than k-omega in this case, because we have the mesh, coarse mesh, poor mesh, and our settings we don't want to use. And let's change the fluid. Here you can set the user's parameters of fluid, and you can choose the fluid from database. Let's copy the water liquid with default property of fluid, density, viscosity, and another. Let's create copy and close. Here you can see the fluid one. Let's delete it, and we have the water liquid with density and viscosity. Let's hide it and go to the cell zone condition, and here we have to set the default fluid material. We have to use the water liquid. Here we can set the rotation, some settings for rotation. We doesn't have it here. And so let's go to the boundary condition settings, the inlet. For inlet, let's set 4 millimeters per second condition. It will be constant average velocity on the inlet, and the turbulence property, turbulence intensity and viscosity ratio 10. Okay, let's go to the outlet. Here we have the pressure, static pressure on the outlet patch. Let's set it 1 atmosphere in Pascal for outlet case. And for backflow, if we have the backflow for our case, we will be using the boundary condition total pressure, but in our case we have only forward flow. Okay, wall, we have to set the no slip. It means the velocity equals to 0, and here we can set the ruggedness height, but for this case we will be using the smooth wall of the diffuser. So let's create the named expression. Here we have to create the expression for calculation the losses between the inlet and outlet surfaces. Let's use the average function, and for average function we will be using the absolutely mass flow rate weight. This will be perform the correct averaging of our total pressure. Here we have to set the patch. It will be the boundary zone, outlet patch or inlet. Let's choose the inlet patch, and for this line we have to set the total pressure. This function will perform the averaging of total pressure on the inlet patch with averaging using the absolutely mass flow rate. So we have to make the minus the averaging pressure on inlet minus the averaging total pressure on outlet, and it will be our losses of energy for incompressible flow. For this case, let's check and click OK, and we have our expression. Let's go to the method and choose the scheme simple. This is segregated solver of the CFD simulation. We have to change these schemes. For high accuracy we have to set the second part, and for relaxation factors we will reduce some factors. It will increase the stability, but it will decrease the speed of simulation convergence. You can change it when you perform several simulation, for example. Let's go to the residuals, and you can the criteria of convergence of simulation. Let's set it smaller and click OK. Let's go to the report plot, and here we have to show during the simulation of our pressure, total pressure loss for our diffuser. Let's go to the expression report definition, and let's set the loss total pressure our function. OK, and add it here. plot it and print to console. Let's call it loss total pressure. And click OK. And here we have the report plot of our loss of total pressure. Let's make the hybrid initialization of initial fields values. It will perform some very potential flow simulation with 10 iteration, and go to the calculation, run calculation, set the 1000 iteration and click calculate. So we will run the simulation. For here we have run the simulation. Here you can see the residuals. The criteria is 1.0005, and here we have the expression for our loss total pressure. The value of loss total pressure you can see also in console is this value 565, and this during the simulation we have the constant value of loss total pressure. It means that we have the convergence of our value of loss total pressure, and we have the very small residuals for velocity residuals k and epsilon. For continuity we have the not so small value of convergence, but I think it is enough for our simulation. Let's stop the simulation because our loss total pressure is converged. We have the constant value with iteration, it doesn't change. Okay, let's click the stop and let's go to the scene and create the contours, and let's visualize our parameter flow. For this we will create the planes, YZ plane for diffuser. Let's click create, and ZX plane. Let's click create, close, and for these two planes let's create the flow fields. Let's check it and save and display. Here you can see the contours of static pressure. How can you see our static pressure is changed from inlet to outlet? It will increase because the diffuser increase the pressure, static pressure, and decrease the velocity. It's true for this simulation. You can see this value, it is in 0.9 atmosphere and 1 atmosphere for outlet patch. Let's create the total pressure, save and display, and here you can see the full energy for incompressible flow, the total pressure, and the difference between this patch and this patch, it is loss between inlet and outlet, loss of the energy through the diffuser. Okay, go to the contours and let's visualize the velocity field. It will be the magnitude, the full value of velocity vector. Okay, and you can see that for inlet patch we have the 4 meters per second, and for outlet is 2 meters per second. It means that the diffuser decrease the velocity from inlet to outlet and increase the pressure, static pressure of course. And for total pressure we have the losses. Here we have the some gradient of our velocity. If we will make the more angle for diffuser, we will get the more blue field. Okay, Our loss is 565 Pascal. Thank you for watching. Subscribe to the channel. Goodbye.